Talking now about summations. First, let's introduce, maybe also you have seen this, but just do some recall. When we say we have a term am plus 1 an from the sequence an, so what does it mean? And we need to sum up all these numbers, so we can simply do sum from j equal to m until n aj. So this means that we will start by am, then we will sum it up with the am plus 1, and then with the am plus 2, then with the am plus 3, then with the am plus 4 until we reach an. Okay, so it can be written like this: j equal m to n, or this way j equal m to n, or just say j between m and n. And this actually represents what I said: am plus 1 plus an, okay, until we reach an. And the variable, actually, what is the variable j? Is just called the index of summation, okay, and it runs from the lower limit, that is m, until the upper limit, that is n, that is also included. Both are included. More generally, we can also say sum from j, the sum of aj with j belongs to s. So here, because what we have seen here is just j actually goes from m to n, but here actually doesn't go from m to n. It just it will be just equal to all the elements in the set s. So for example, if s is equal to 2, 5, 7, 10, saying that this will be equivalent to a2 plus a5 plus a7 plus a10. Okay, so it will be equivalent to this expression here. Here are some examples that you can see that are simple, actually. So we have some useful, actually, formula for summations that are these formulas. For example, the first one, which is here, which is the which is actually the geometric progression, or the geometric series. We have, and this actually you have seen in high school, from the sum from k equals 0 to n of a r k, for r different from 0 for sure, is equal to a r n plus 1 minus a over r plus minus 1. So this actually we can use when we have a sum like that. We have, let's say, for example, I don't know, what you can face this, the closed form solution, or this will be equal actually to this expression. And what we have seen and proven is this one, the insertion sort, when we was trying to find or when we were seeking the solution of the worst case scenario, when we were trying to find the complexity, actually, or the cost so we proved that the sum from k equal 1 to n of k is equal to n multiplied n plus 1 over 2. Just please revisit the first chapter and to just see this one. This was actually in the handwritten on PDF. I will provide you with the extra sheet. I will put them on Moodle today or maybe tonight. Another one is when we have the sum from k equal 1 to n, k square will be equal to this one. Okay, we didn't prove this, but this can be proven actually by induction. N multiplied n plus 1 multiplied to n plus 1 over 6, etc. You can look into these, and these can be useful. Maybe not in our problems, but in other problems that you can face. Okay, so this is actually about sequence and recurrence relation. Let's now talk about mathematical induction. So we continue with the mathematical induction. What is actually the mathematical induction? Suppose that someone asked you, prove that you can reach the end of ladder. You say, this is obvious. I can go to the first step, then From the first step, I can go with the second step, then I go with the third step, then with the fourth step, until I reach n step, and then I can reach n plus 1 step, and going this way, we can reach the end of a ladder. And this is actually true. So we can reach the first rung with the first step, then with the second step, we can reach the next rung. And you say, okay, so if I can reach a particular rung, then I can reach the next rung with one step further. So from 1 we can reach the first rung, then by applying 2 we can reach the second rung, by applying 2 again, the third rung, until we reach the upper bound of the end, or the end of the ladder. Okay, so this is just an example, just an analogy from a real life example. Now let's say, what is actually the principle of mathematical induction? Actually, this is a proof that is widely used in mathematics. So the principle of mathematical induction is to prove that Pn is true for all positive n integers. So we need to have Pn equal to something, or An equal to something. We need to prove that this is true, okay? And to prove that, the way is the following. When we say induction, the induction way is the following. So you prove the first step, or the base step, so showing that the initial step, that can be P1, P2, depends on the problem, but it's usually P1. Just prove that this is true, given Pn. So if An equal to 3n minus 1, just prove that for the n equal 1, that P1 is true, okay? Then the inductive step is the following. So given that Pk is true, so we assume that Pk is true, we say, okay, the relation for k is true, then I need to prove that, given actually that relation Pk is true, I need to prove that Pk plus 1 is also true. So if you complete actually these two steps, the base step and the inductive step, so you prove that Pn is true for all positive integers. Okay. So to complete the inductive step, assuming the inductive hypothesis that Pk holds for an arbitrary k, and show that k plus 1 must be true. Okay. So to go back to the example, climbing an infinite ladder example. So the basic step is that you can reach the first rung, and then the inductive step is that you say, okay, given that I can reach the rung n, going one step further, I can reach the rung k plus 1 or n plus 1, whatever. Then here you prove that Pk is true. Okay, so you can, for any k, Pk is true. Okay, but to just also to express this mathematically as the rule of inference, so it's this way: P1 is true, and this is the first condition. P1 is true. If you prove that this is true, then you prove that for all k, okay, Pk true implies that Pk plus 1 true. So given that Pk is true, you prove that Pk plus 1 is true. So this is actually means that Pk true implies Pk true, and this will be true. So, and if P1 is true, so true and true will give you a true, and this will imply actually a true will imply a true. So here we have proved that for all n, Pn is true. Okay. So this is just to express it as the rule inference. But what we are going to do, we are going to start with examples. I mean, we can also take the example of dominoes. So given that the first the first domino, when you knock down, so it will this will be true. Then given Pk is true, is knocked down, then Pk plus 1 will be also knocked down. And then here we have proven that Pk is true. Let's go directly to see some examples here. If we ask you, okay, this one we have proven this one, the sum from I equal to 1 to n of I is equal to n multiplied n plus 1 over 2. So to prove this, you say, okay, let's consider the case n equal 1. So if n is equal to 1, so this is 1, and this is true because 1 multiplied 2 multiplied 1 plus 1, 2 over 2 is equal to 1. So this is actually true for the case when n is equal to 1. Okay, so 1 multiplied 1 plus 1 over 2 is equal to 1. Now you will assume that for n, the case this is true for n, and we have to prove that this should be true for n plus 1. Okay, so for k plus 1. So the hypothesis is this one. This is true. We assume that this is true. Now we have to prove that for k plus 1 this will be true. Actually, if you put k plus 1 here we will get k plus 1 multiplied k plus 2 over 2. Just replace k plus 1, k with k plus 1. So you have to find that the summation or the sum from I equal to 1 to k plus 1 of I is equal to k plus 1 multiplied k plus 2 over 2. Okay, so to prove this, let's start from here. So the sum from I equal 1 to k plus 1 is equal to 1 plus 2 plus k plus 1. Okay, this term here, this part is what? This part is the sum from I equal 1 to k of I. Okay, and we know that this part is equal to k plus 1 over 2. So just to replace this part here with k multiplied k plus 1 over 2. So this will give k plus 1 over 2 plus k plus 1. Just develop this one, you will get k plus 1 plus 2k plus 1. Just to multiply 2 by here, and this will be summed up with this. And this expression is equal to k plus 1, k multiplied k plus 2 over 2. Okay, and this is actually what we need to prove. So we prove that the sum here, the sum from I equal 1 to k plus 1 of I is equal to k plus 1, k plus 2 over 2. And this is equivalent to this one when you replace k with k plus 1. So given that this is true, we showed that the k plus 1 is also true. And then we can say, okay, so this has been proven true. Okay, so the first time we guessed this, and here we proved that this is true. Another case or another example, you are asked to conjecture and prove correct formula for the sum of the first n positive odd integers. When we say the first n positive odd integers, the odd integers are 1, 3, 5, 7, 9, 11, 13, 15, 17, etc. until we reach n. Okay, so first we need to conjecture this. So to conjecture this, let's say, okay, for n equal to 1, we will get 1 is equal to 1. For n is equal to 2, so we'll have 1 plus 3, okay, which is equal to 4. For n equal to 3, we will have 1 plus 3 plus 5, which is equal to 9. For n equal to 4, we will have 1 plus 3 plus 5 plus 9, because we know that the odd integers are 2n plus 1, okay, 2n plus 1. So for n equal 1, for n equal 0, 2n plus 1 is equal to 1. For n equal 1, or we can consider it as 2n minus 1, okay, 2n minus 1. So just say that the odd integer is 2n minus 1. So for n is equal to 1, we will get 1 equal 1. For n equal to 2, we will get 1 plus 3 equal to 4. For n equal to, because we are talking here about the sum of the positive odd integers until n, okay? So for n equal to 2, we will get the first odd integer, which is 1, the second odd integer, which is 3. For n equal to 4, for example, the first 4 odd integers are 1 plus 3 plus 5 plus 7. When n is equal to 5, we will have the first 5 odd integers, 1 plus 3 plus 5 plus 7 plus 9, which is equal to 25. For n equal to 6, we will get 1 plus 3 plus 5 plus 7 plus 9 plus 11, which will give us 36. Okay, here you can find that 1 is what is 1 square, 2 is 4 is 2 square, 9 is 3 square, because here n is equal to 3, here n is equal to 2. When n is equal to 4, 16 is 4 square. When n was equal to 5, 25 is 5 square. After that, it was 36. When n is equal to 6, we got 36, and 36 is 6 squared. So every time we are getting that the sum is n squared, okay? So 1 plus 3 plus, we got this one, this is equal, we guess actually that this is equal to n squared. Now this is what we guessed. Is this true or not? We can try to prove it. How to prove it? Using induction. Now let's say using induction, P1 is true, okay? So P1 when n was equal to 1, 1 is equal 1 square. So when n equal to 1 here, 1 square is equal to 1, and it is 1. So here we have proven the first base step. Now the next step is to say that given that k is true, we need to prove that k plus 1 is true. When we say that pk is true, it's like saying that the sum of the first k odd integer is equal to k squared. We need to prove that the sum of the first k plus 1 odd integer should be equal to k plus 1 squared. Okay. So what is actually, so the inductive hypothesis is that the sum to k is equal to k squared. Now we need to show that the sum to k plus 1 should be equal to k plus 1 squared. Okay, so the sum to k k plus 1 is 1 plus the number after this one will be plus 2k plus 1. Okay, this is actually the sum for, this is for k plus 1, the odd integer. So the sum of all elements until k plus 1 odd integer will be this one. We can replace this part, we can replace it by k squared, so we'll get k squared plus 2k plus 1. Okay, k squared plus 2k plus 1 is simply equal to k plus 1 squared. Okay, so we proved that the sum of the first k plus 1 is equal to k plus 1 squared. So since this is true, given that the sum to k is equal to k squared, so now we can say that this is actually correct. Okay, hence we have shown that pk plus 1 follows from pk. Therefore, the sum of the first n positive odd integers is n squared. Okay. Now, take another example. Use mathematical induction to prove that n is less than 2 to the power n for all positive integers. Okay, this is this is great to prove that. Is this obvious? I don't know. Let's try it. Let's prove first the base case. The base case is for n equal to 1. When you say positive integers, and starting n equal to 1, because this is integer actually. So is 1 less than 2? Yes, this is true. So here we have proven the base case. Then the inductive case, you say, okay, given that n is less than or k is less than 2 to the power k. So we have to prove that k plus 1 is less than 2k plus 1. 2 to the power k plus 1. Okay, how to prove that? I mean, it is not difficult, because k plus 1. Okay, so we need to prove what is that k plus 1 is less than 2 to the power k plus 1. So k plus 1 is less than what? K is less than 2 to the power k. This is, we know, right? Because this is actually the hypothesis that k is less than 2k. So k plus 1 will be less than 2k, 2 to the power k plus 1, and 2 to the power k plus 1 is less than 2 to the power k plus 2 to the power k, okay, because 1 is less than 2 to the power k, obviously, and then this can be written as 2 times 2 to the power k, okay, because this a plus a is equal to a. So this one plus this one is equal to 2 multiplied 2 to the power k. 2 times 2 to the power k is equal to 2 to the power k plus 1. So we have proven here that k plus 1 is less than 2 to the power k plus 1, starting from the hypothesis k is less than 2 to the power k. So therefore, n is less than 2 to the power n for all positive integers. Okay, let's take now this. Okay, we still have 2 examples, and we are done. We will be done with this. Using mathematical induction, prove that 2 to the power n is less than n factorial for every integers n greater than or equal 4. So the base case here will be for n equal 4, because starting this integer. Now we can say, okay, we can say 2 to the power 4 is less than 4 factorial. Why? Because 2 to the power 4 is equal to what? It's equal to 16. And 4 factorial is 4 times 3, which is 12, times 2, which is 24. Okay, so 16 is less than 24. So the base case is true. Okay, because 2 to the power 4 equals 16, less than 4 factorial, which is 24. Now we assume that the inductive hypothesis that 2 to the power n is less than n factorial, that we assume that this is true. And we need to prove that 2 to the power n plus 1 is less than n plus 1 factorial. How to do that? Okay, so now let's start with 2 to the power k plus 1. This is equal to 2 times 2 to the power k, okay? And we know that 2 to the power k is less than k factorial. This is actually the hypothesis when we consider that that this is true for k, and we are proving that this should be true. This is true for k plus 1. So 2 to the power k is less than k factorial. This is true. So 2 times 2 to the power k is less than 2 times k factorial. And we know that for n greater than 4, okay, 2 is less than k plus 1, right? 2 is less than k plus 1, because k plus 1, if k is equal to 4, so this is equal to 5. If k is equal to 5, this is equal to 6. So this is always greater than 2. So this is less than k plus 1 k factorial. And this is equal to what? This is equal to k plus 1 factorial. So here we proved that 2 to the power k plus 1 is less than k plus 1 factorial given this hypothesis. So starting from here, we proved that if this is true, 2 to the power k plus 1 is less than k plus 1 factorial. So if pk is true, pk plus 1 is true, and therefore 2 to the power n is less than n factorial for every integer, and this is true. Okay. The last example is this one, is the following. Using mathematical induction, we need to prove that n cubed minus n is divisible by 3 for every positive integer. Okay, that's interesting. How to do that? Okay, simply by induction, we say assume the base case. The base case is, for instance, it is for every positive integer. The base case is when n is equal to 1. 1 cubed minus 1 is equal to 0, and 0 can divide 3. 0 divided by 3 is equal to 0, so this is true. Then we assume that, okay, this is true for k, okay, and we need to prove that this should be true for k plus 1, okay. So for k plus 1, this is actually k plus 1 cubed minus k plus 1. So we need to prove that if this is true, k plus 1 cubed minus k plus 1 is also divisible by 3. Okay, let's see how to do that. K plus 1 cubed minus k plus 1 is equal to, just develop this one. This one would be equal to k cubed plus 3k squared plus 3k plus 1 minus k plus 1. Okay, so just take k cubed here minus k. Okay, so we'll get k cubed minus k, then plus 3k squared plus 3k here, plus 1 and minus 1 will be just cancelled, the 1. So we'll get k cubed minus k plus 3 times k squared plus k. Okay, we know that k cubed minus k is divisible by 3 because we assumed that this is true. And now we know that this term also divides 3 because 3 times any number is divisible by 3. Simply divide this by 3, you will get k squared plus k. Okay, and so this is divisible by 3, and this is divisible by 3. So the whole expression here is divisible by 3. Okay, then we proved that this one for the case k plus 1, if it is true, then we can say that n cubed minus n is divisible by 3 for every positive integer. Okay, this is actual Fibonacci number. I will not go into details because we don't need to do this one. You can just skip. Then solving recurrence, we have the substitution method, the recursion tree method, and the master method. The substitution method is the one we are using, where we guess a bound and then we use mathematical induction to prove our guess. And that's actually what we did. So we do a guess. I mean, the guess is not randomly done. However, we just follow some logic way to do some guess. Then we say, okay, let's prove that this guess is true using mathematical induction. And then this is what we call substitution method. There's another method that is called recursion tree method. This one is actually similar to what we did in merge sort, but I will not go into details for this one, and I will not discuss the master method. Okay, so some slides are for the substitution method, so you can see them. And now, once this part, I think, and I hope it's clear, we'll go to the next part, that will be the recursive algorithms. And thank you for your attention.